All right, we're the phone is out of memory. I forgot to. Actually, I deleted the photos, but done with it. Don't worry about the excuses. Anyway, we're keeping this. Can keep continuing on this. If the period for this to go through one cycle is 0.1 second, the frequency is 10, right?
Yeah.
What's the unit?
10 times per second.
Yeah. What's it actually called? No. What's the unit in second for frequency?
Like, I have no idea.
No. Time is right.
Yeah.
Actually, normally is written as capital T just to show it's not a variable; it's a constant. What's the unit for F? What's the
1
unit
over second?
Right, yeah, 1 over second. Right? And actually, this is not good. It's 1 over second, right? This is called what?
The inverse of time.
Does that help?
Don't know what that means.
Hertz. Your frequency.
When
you listen to they say 105.3 or whatever. You know what that is? Frequency. It's hertz. Okay, it's probably kilohertz or megahertz or whatever. It's not just hertz. Hertz is too slow. Okay, where's the joke?
Pizza Hut.
Oh, Pizza Huts.
That's Pizza Hut.
Hertz.
Never mind, it's just this
Okay, whatever.
online thing.
All right, now. So you know the period is 2 pi over omega, right? So frequency is what? 1 over this, right?
Yeah.
2 pi over omega. This is omega divided by 2 pi. In other words, omega is basically 2 pi times the frequency.
Mm-hmm.
We call it omega because in all of these things, right, we're going to see omega, not the F. There's a 2 pi in it. We call it angular frequency. Just a way of calling something. So now, okay, so now, in other words, okay. Also, when this is something cosine plus something sine, you know what this end up? What's the situation here? Let's say cosine. Let's just say sine. Whatever. Let's say sine omega t plus a whatever. How do you call it? The leftover angle? Let's call it alpha, right?
Yeah.
Right. We open it up. You know what? When this open up is what?
I don't know.
You can cheat. Open up this bracket. Go cheat.
Oh.
Go cheat.
You can make it something.
Go cheat.
Yeah, that.
Okay. And then you can multiply this by an A, right? Then A multiply this, A multiply this.
Yeah.
Yeah. This is what you have is C1. Look at this. C1 equals to A cosine alpha, C2 equals to A sine alpha. Yeah?
Yeah.
This is doable. You can figure this out. Because, you get what I'm saying? The alpha can be figured out because C1 squared plus C2 squared is A squared.
Yeah.
Right? So what we're talking about is this situation. This is C1, this is C2, this is A. This is alpha. Right? You have the C1, C2, you can definitely get A and alpha. That's the situation here. You see it? In other words, for this, right, you can get to another oscillation. All you're doing is changing the amplitude because this amplitude is C1 and C2, right?
Yeah.
And this amplitude is basically this amplitude squared plus this amplitude square square root, right? And then also there is the angle change, the shift from omega t to somewhere else, but doesn't matter.
Yeah.
All you're looking at this oscillates as a angular frequency omega. This is the angular frequency omega. This is also just there's a shift. You know. Now, this could be anywhere. You know, somewhere there's a shift going on. Yeah.
Yeah.
Still same. All we care about the amplitude, right? I mean the frequency, angular frequency, right? Or frequency. Frequency is the same. And this frequency has something to do with. Did I write a clean one? I didn't. Okay, just write it here. Look at this. Omega equals to K divided by M. Right?
Yeah.
It matters about the spring, how strong that spring is. Right? Also matters about the M, how much mass you attach to it.
Yeah.
Then it doesn't matter what your initial condition is, or however whatever it is, and that angular frequency will not change.
Yeah.
Yeah. Now, I'm not gonna get into the in high school physics. I think when you get about this, they spend a lot of time on once you have this sine and cosine, they spend a lot of time on they spend a lot of time on whether you push a spring on over, right, and let the spring bounce back. Then what's the velocity here? And stuff like that. Actually, you know what? Let's just do one. Right? Let's just do one. Let's say you have a spring, right? This is a f equals to the k equals to 1 minus x. Let's just say that, right? And the mass is 1 kilogram. This is everything in 1. Yeah, and then you move this 1 meter. Probably is too much, right? Just do 1 meter. You shift this 1 meter and see what's gonna do. Yeah. This is all about the initial condition. So now, look at this. If k, m, everything equals 1, omega equals 1, right?
Yeah.
And then you have some kind of a mixture of sine, cosine, whatever, right? We call this 1. We call this stable. We call this x, right? This is x. We call this stable position 0. Yeah. Now you pull this over 1 meter. Okay, at time 0, this thing not moving here.
Okay.
Right? In other words, this is going to be at the time 0. This thing now moving, speed 0, but position is minus 1 meter, right here.
Yeah.
Right? then you want to know when this thing gonna swing over and cross this, cross 0. You know,
Yeah.
that's kind of a simple thing to do, right? Because now this if this is 0, you know this is sort of a minus cosine situation, right?
Yeah.
This is speed is 0, not moving. So this is the extreme of this. So you know the x is something cosine omega t. Actually, just something cosine t, right?
Yeah.
And then that something is 1.
Uh.
We just said it moved 1 meter, right? So x equals to just cosine t, right? And let's say they ask you when is it gonna hit here, right?
Yeah.
So when is it gonna hit here? T equals to
Cosine 0.
no.
Oh.
This is t. When this thing gonna hit here?
Like pi over 2.
Exactly. Pi over 2, right? What's the velocity at this point?
Like 1.
The velocity is 1. V equals to 1. How'd you get that?
Because like if it's just cosine, then like at that exact middle point, the slope is 1.
Oh, okay, yeah. Okay, yeah. I wouldn't. Okay. Let me do it my way. Okay. You want to do the x dot, right? That's the velocity, right?
Yeah.
Velocity is cosine t. Let's take a derivative.
Negative
That's
sign, minus sign, whatever.
yeah. Right?
Yeah.
No. Sorry. This is minus cosine. A is minus 1 because at the time t, this is minus 1.
Oh, okay.
Right? So minus is positive. Sorry about that. Okay. Now, when this t equals to pi over 2, this equals to 1. Right? At that time, this equals to 1. So the velocity is 1, which is correct. Okay? Okay. At this point, what's the acceleration?
Sure, 1.
Acceleration 1.
Wait.
Okay. You want to cheat, right?
Yeah.
You know, when this spring is, well, if this thing is not moving here, right? What's the force on it?
It's 0.
0, yeah. When it swings back at this moment, there's no force on it. It comes through this, is moving through it. But at this moment, you know the force is 0, right?
Mm-hmm.
You know the acceleration is 0.
Yeah.
You want to cheat. Now let's calculate this.
Just take a derivative of that sine t again.
Okay.
And cosine pi over 2
Cosine pi over 2 is what?
is like 0.
Yeah, right. Yeah. Acceleration at this point is 0. Okay. Okay.
Yeah.
And so on and so forth. You can do whatever. And then there's a okay, whatever. We're not going to do it. There is a thing that this time they always, in your physics books, they always introduce a kinetic energy or whatever. They use energy to do this stuff, by the way. They don't use this because they don't have they don't do integrals or derivatives. But anyway, we'll do that later, just to make a connection between this and your textbooks. But now let's move on. Let's say the F equals to minus kx, right? This is your spring.
Yeah.
Now you have a resistance. That resistance is proportional to speed.
Yeah.
Right? The faster it is, you have this experience, right? The faster you run, you have more, you feel more resistance on you, right? So you also have the resistance. That's minus the speed. Whatever the speed, the direction of the speed, you get it minus of that.
Yeah.
Right? This equals to, of course, m dx dt, right? right?
Yeah.
So you clean this up a little bit. This is all constant, right? I'm not gonna just do it. I'm just gonna okay. You can move this all on one side, and then divide it by m. So this is all become constant, right? So we have x2 dot plus bx plus c equal to 0, right?
Yeah.
Where b equals to alpha over m, c equal to k over m. Okay.
Okay.
Now same deal. We'll say x equals to e lambda t, right? Put it in, right? Lambda squared plus b lambda plus c equal to 0, right? We've done this before.
Yeah.
Remember? So now we solve for this, right? We solve for lambda 1 and lambda 2, and then we have this thing, okay? And then we will get them all out, this and that, okay? X equals 2. I'm going to save all this. Some kind of amplitude, you understand that, right?
Yeah.
And then, okay, lambda equals to minus, okay, a is 0 minus b plus or minus b squared minus 4c, okay? In this case, because these are all
Over 2.
real numbers, there's going to be numbers.
Isn't it over 2?
Oh yeah, over 2, right? This is going to be imaginary number.
Yeah.
Okay, this is the real number.
Uh-huh.
Okay, this is going to come out, and I'm going to put it all back. It equals to this. Alpha over 2m t cosine k over m minus alpha squared 4m squared this much t plus some kind of a angle. Okay, we don't care. In this situation, where's that situation? Yeah. In this situation, we don't care about what a is really that, or the initial angle is. This we don't care about. Okay, let's write this over again. This is 0. Okay. These are all just initial conditions.
Yeah.
So for now, we don't care. We'll figure it out later. When you have a real situation, just like the example just now, we have those, right? So here, we don't care about the a, we don't care about this phi 0, right? So now, look at this. This moves with this angular frequency, and look at this. This is interesting. The amplitude goes down exponentially. As t goes down, the amplitude goes down, right? Has something to do with alpha, something to do with m, or whatever, something to do with k, whatever. You see this?
Yeah.
Yeah. In other words, this thing goes like this, right? If you pull it somewhere, right, you pull it, then let it go. Yeah. The amplitude will go down. The frequency doesn't change, like that. It's damped movement. Yeah?
Yeah.
Okay. Let's do this in another way. Let's say mx 2 dot. This is f, by the way, yeah?
Yeah.
This is f. Equals minus kx. Still minus kx, right? Instead of give it resistance, we actually give it a force. Okay? We give it a force. We call it F0 EI omega t. We'll give it a force.
Yeah.
Okay? This is periodical force. Okay? Let's see how this is going to work out. Okay? Same situation, you do this and that, whatever. You understand that these two are the same thing, exactly the same thing. You just have a constant going. Let's see how much I want to do this. There is, okay, the way we solve this, oh yeah, there's one thing that's different, because what we did before, we get it to all be all zero, right? Now we have a term here that doesn't have x in it.
Yeah.
It's not like x2 dot plus something x dot plus x equals 0. This is the leftover. This is the t. This is like a gt situation. Okay. To solve this kind of equation, x2 dot plus x dot plus x equal to g, right?
Yeah.
The way we do it, we solve this equation, x2 dot plus x dot plus x equals to 0. We solve for all solutions in this. Then we find one solution for this.
Okay.
Then add these solutions up. That'll be the all solution for all of this. You get it?
Yeah.
Yeah. So we solve for the one without this term, which is you know what it is, right? A cosine omega t plus, right? That.
Yeah.
This is for this solution. Now we just need to find one solution that fit that. We make let's see. Let's see how I want to do this. Okay, let's just do this. Let's call this. Okay. On the in the in this one, we call this k over m as omega, right? So we just keep doing this. K over m. We have two omegas here. This k over m. I'm gonna do the same with my notes so I don't get totally screwed up. K over m. I call this natural frequency of the spring. Okay.
Yeah.
We call it omega. Okay, we call it omega 0. So this is the solution of the free situation is this.
Okay.
Yeah. In order for me to find that unique one, I'm gonna just let's see. I'm gonna just call this x equals to a, some kind of amplitude, e I omega t. Okay.
Okay.
So we put into this. That becomes, omega comes out twice. This becomes minus omega squared a e I omega t, right?
Yeah.
This move over become positive k plus k. K is omega squared. Let's just do kx, right? Equals to f 0. Let's see, this divided by m, this divided by m. E I omega t. Okay, now this I didn't count this m. I just put x, right? I divided m, so the x2 dot, this is x2 dot, right?
Yeah.
Then that m divided by here, I just leave it here, right? Oh yeah, actually this is a e I omega t, right?
Okay.
And this e I omega t. Yeah.
Yeah.
So now I can I just okay, I just do it. Doesn't matter. Take this e I omega t out, right? This is a. I can take a out, right?
Yeah.
And this is omega 0 squared. Okay. Then let me just rewrite one more step. So this is minus omega squared a plus omega 0 squared a equals to f0 over m. Yeah?
Yeah.
A equals to, divide this over, omega 0 squared minus omega squared over f0 m. Okay?
Yeah.
This actually fit this function, this unique function. I'm just giving one. It fits, right? It works out. Yeah? You understand this? I just call this a, then I can find a, and omega is just that force, the frequency of the outside force. Yeah, it's different from the what I call natural frequency of the spring. Okay, and then I found this a. That means when a equals to this thing actually fit this equation. So the equation, the real solution for these equations, the x equals this plus this, mixture of this and this, right? This could be anything because this is a spring. It moves at this frequency, and then it's another factor that move at this frequency. Okay, but let's just look at this solution. The amplitude is a, right?
Yeah.
The a equals to this. What happened if this outside force omega equals to the what we call the natural frequency of the spring? What happened?
Wait. The resistance like stronger.
There's no resistance here, by the way. Just to be simple, there's no resistance is the x dot term, right? I don't have the x dot term. Just make it simple, because we just studied the x dot, right? You know the x dot situation, right?
Yeah.
It's you know, if x dot is just here, just like this, right? You just with this term in it, right? I don't want this to mess this thing here. We just say if it's a no friction spring with the outside force at this omega impacting on it, right? What's gonna happen is this solution, which is the solution for the 0 one, and the unique one here. This is the unique one. I just make one, and this works. This solution works, right? And then a for this solution, right? A equals to this.
Yeah.
But my question is, what is omega 0 if omega 0 gets put it another way? If this is the outside force, right? The frequency of the outside force, right?
Yeah.
If the outside force getting close to the omega 0, what happens?
Then it's like getting the like the frequencies are getting smaller.
No. The spring has a natural frequency.
Yeah.
In other words, you press it, it's gonna swing in a certain way, right?
Yeah.
That's the frequency, right?
Yeah.
Now, what I'm saying is, you put an outside force, the frequency of the outside force, let's say equals to this natural frequency of the spring.
Yeah.
What's gonna happen to the amplitude?
It's gonna be like nothing.
Because what? Look at this.
Subtracting, or they'll be undefined.
Let me get it even closer to you, okay? When this equals to this, omega sub 0 equals to omega, what happened to A?
It's undefined.
Okay, let's drop the year. Okay, let's say very close, but not 0, not exactly 0.
Well, it becomes infinitely big.
Yeah. You see this? When you have a spring, right? the spring has a natural frequency, which is this.
Yeah.
If you put an outside force of the same frequency to it, the amplitude is going to infinity. Not going to be right away, but every swing is going bigger, going bigger, going bigger. You get it? The amplitude, this is forever. This is forever. This is after the time to infinity. This is that solution.
Yeah.
Initial solution be some kind of a mix, but doesn't matter. You get this?
Yeah.
When omega equals to, when you're outside omega, you use the equals to omega 0, the amplitude is going to go to infinity. Yeah?
Yeah.
Did I say when you run, you want to look for, when your body has a natural frequency. When you take a different posture, the natural frequency changes.
Yeah.
You understand? When you're conducting, right? When you change the rhythm, actually you change your body posture a little bit, but you can still go with the natural frequency, right? That's not what I'm talking about. When you run, right, you can get your body at a certain frequency of your comfort. You feel comfortable about it.
Yeah.
And then you use your muscle to give this frequency, every step, obviously. You give it outside force, right? Use your muscle to give it outside force.
Yeah.
If this outside force equals to your natural frequency, right, then your amplitude going to infinity. Going to, not going to get there. That's another thing. When you get there, when you go certain fast, then there'll be other problems, frictions and stuff going to come in, right? But let's just say there's no friction. If there's no friction, what we're talking about, you want the outside force frequency to be the same as the frequency of your natural spring,
Yeah.
which is your body. The reason when you run, right, you really need to adjust the posture of your body. For instance, your arm need to bend a little bit so you can move a little faster. When your arm goes straight, right, you need more force to swing your arm. Yeah?
Yeah.
It's a bad habit to run with your arm straight, right? Take more force to swing your arm. Now, this is very useful. Yeah? When you use any kind of thing, you use force. You want to ask the question, what is the natural frequency of your body?
Mm-hmm.
Can you think of another example for this? Why in a piano or whatever, there are certain when you flip a string, it comes up with a certain note.
Yeah.
That when you flip actually is it's gonna do the natural frequency of that string.
Mm-hmm.
But when you do it, that's the force. Okay, but you never when you play whatever guitar, right? You're never gonna move at the frequency of the frequency the string vibrates. So you just do it one time. Then the string will vibrate at that certain whatever that natural frequency of that string. That give you a certain note. That's a bad example. But anyway, okay. I'm gonna just write this up. Okay, this is just for whatever it is. The solution is x equals to a cosine omega 0 t plus f0 over m. Yeah.
Yeah.
This is the solution when you have an outside force on it. The outside force is omega, and the natural frequency of the spring is omega sub 0.
Yeah.
Yeah. In other words, if you have just make a general comment that if you put an outside force, F0, that's your ability. Your muscle, your whatever. That's the force. You want to make most impact on the spring. When you have the ability to put F0 on it, you want to make an impact on it, you better put this F0 at the angular frequency, at the frequency of the spring. You do it one time, when I go with the spring. That makes the biggest impact. This term. Okay?
Okay.
And when omega goes to omega 0, this become omega 0, this will become omega 0, this is just become a harmonic oscillation. This is the sine cosine omega 0 kind of a motion. Okay? That should be it. Bye.